Time. It's everywhere. It impacts every aspect of our lives. But how can we harness the awesome power of time to analyze and predict the behavior of systems? In this video, I'll give you a high-level overview of how you can use time series modeling to get the insights you need by analyzing the past, understanding the present, and predicting the future. Time series data is a sequence of data points recorded at specific moments in time. We can create models with this data for a variety of applications, like tracking sleep patterns, optimizing home energy usage, or predicting when a wind turbine will need repairs. Time series modeling enables us to do these things in three key application areas. First, pattern recognition, where you analyze time series for known characteristics, like trends that occur over time, or cyclical variations that repeat at regular intervals. By recognizing the recurring patterns in your sleep over multiple days, your smartwatch can determine whether you had a good night of sleep or a not so great one. Ugh. Second, forecasting, where you can use existing data to predict future trends and act accordingly. An electric vehicle charging in your garage can utilize existing daily home energy usage to predict the house's lowest electricity usage hours, so it can charge overnight at the cheapest rates, as you hopefully get a good night's sleep. Third, anomaly detection, where you spot unexpected behavior in a time series that might signal impending issues. Sensors in the gearbox of a wind turbine can collect time series data on how well the turbine is functioning. Anomalies can be early warning signs of needed repairs before anything breaks or, explodes. So that's the why of time series modeling. It's time to dive into the how. To get started with time series modeling, first, we need training data. This is historical time series data that our model uses to learn the characteristics of the series. Before we can train anything with it, though, we usually have to pre-process it. Basically, our data can be messy, and we need to clean it up by, among other things, removing background noise, filling in missing data, and selecting the most meaningful features. With our data pre-processed, it's time to build our models. A model, such as a neural network, is a mathematical representation of a real-life system, which learns how to represent the real system by extracting patterns from the training data that we've processed. Once the model is trained, we can use it with new data as inputs. This data, pre-processed of course, is what the trained model analyzes to achieve a goal, like recognizing patterns, detecting anomalies, or making forecasts, depending on the model's characteristics and what we trained it to do. Now that our data and models are ready for takeoff, let's take our analysis to the skies. Ladies and gentlemen, this is your captain speaking. Welcome aboard MATLAB Airways, where it's always a good time to model systems over time. On our aircraft today, we have the latest in time series modeling methods to make your flight as smooth as possible. Let's take a tour through this hypothetical airplane and see some potential time series modeling methods in action. In the baggage compartment, we're looking to forecast baggage amounts for upcoming flights based on previous baggage weight data. One option that could work here is the statistical method ARIMA. The autoregressive integrated moving average is a statistical model that can use existing data to predict future values, capturing both trends and cyclical variations. This way, the airline can know in advance how many baggage handlers are needed and how much time it will take to load all the bags, so the plane can leave on time. Up in the plane's cabin, the climate controls need to recognize patterns in the air pressure and react accordingly. These fluctuations are caused by changes in altitude, temperature, or other conditions. One possible solution for this is a support vector machine, or SVM. SVMs are supervised machine learning models that can effectively model nonlinear relationships. Using this model, the climate controls can automatically react to exterior pressure changes and raise or lower the interior air pressure accordingly, avoiding any high-pressure situations during the flight. The plane engine's performance needs to be constantly monitored to detect anomalies. One way we can achieve this predictive maintenance is by using a deep learning method called an LSTM, or long short-term memory network. This model retains important information and discards irrelevant information over time, allowing it to capture long-term trends. In this way, it models normal engine behavior. Before any actual problems arise and cause any bumpy rides, anomalies and data shifts are flagged by the model when they deviate from its predictions. Then the plane is brought in for maintenance and prepped for takeoff. Having in-depth analysis of the past conditions and current performance of the plane, as well as predictions for those metrics in the future, allows the pilot to chart a course with confidence that a smooth ride is ahead. Systems all over our MATLAB Airways plane work together to get passengers to their destination, and there's a wide variety of time series modeling techniques to use, from ARIMA models, SVMs, and LSTMs, to emerging techniques like transformer models. When it comes to selecting the right approach for your time series modeling problem, explore different options and see what works for you. From recognizing the patterns in sensor data, to detecting anomalies in machine performance, to predicting the future output of our systems, time series modeling unlocks data's hidden insights. Duty calls! For more information on how to use time series modeling to your advantage, or to try these methods out for yourself in MATLAB, check out the resources linked in the description. Thanks for watching, and I'll see you next time.